Alright, so begins our final unit on kinematics, which is stuff that's moving. So from now on, stuff's not going to be moving. It's going to be moving a little bit, but we're not worried about how it moves so much anymore. So today we're going to talk about uniform circular motion. That's stuff that goes around in circles. Bet you could figure that one out, though. So we got, that goes a circle there, circles here. So whenever we go to Six Flags later this year, these are the kind of problems you're going to be doing with a lovely little problem packet. So after this little video, you should be able to describe uniform circular motion. You'll be able to list variables associated with it, determine centripetal force, list different types of centripetal force, and solve problems using uniform circular motion and banked curves. So first, some vocabulary. Anytime you see an R, it's a radius. Anytime you see an M, it's a mass. Anytime you see a V, it's a velocity. F sub c, that little c right here, it's a centripetal force. F sub t is your tension. You should already know that. And what's next? Yeah, sometimes you'll also see it just written as a capital T. But in this section, we're not going to do that because capital T means something different for circular motion. F sub little f, your frictional force. Little t is time. Now big T, which is why we're not using big T for tension, is the period. There's two different kinds of velocity. You're going to have your linear or tangential velocity. That's going to be measured in meters per second. I don't know why I did that. And its formula is this 2 pi r over t. As I said, r is the radius, and this big T is the period. And you're also going to have rotational angular velocity. And it's going to be this weird little Greek symbol that looks like a W. It's actually an omega. And it's measured in revolutions per second instead of meters per second. And its formula is 1 over the period. And you're also going to see an A sub little c, which is your centripetal acceleration. All right. So the motion of an object in a circle with a constant or uniform speed is uniform circular motion. Now these V's that are coming off here, they're tangent to the curve. That's the linear or tangential velocity. So this velocity vector changes depending on where we're at in the curve. Like if we're right here, our velocity vector looks like that. If we're right here, our velocity vector looks like that. It's always a line tangent to the curve, whatever point we're talking about. So we're constantly changing our direction, and if you remember back from kinematics, we're constantly changing our direction. That means we're always accelerating because our velocity is changing. So during, we're going to talk about the period first, that capital letter T. The object repeatedly finds itself back where it started. So if it starts here, it's going to come around in a circle, it'll be right back there. Now the time it takes to do that, to travel to just one full rotation, is called the period. So like the period for the moon is 28 days, the period for the Earth around the sun is 365 days, so those are all periods. And if you remember, the distance equals rate times time, or speed times time, or velocity times time. So we solve that for time. You get time equals distance over rate. Now the distance are 2 pi r, which is the circumference of a circle, which makes sense because our distance is one full circle, divided by our velocity. So since we're not using time, we're talking about time as one revolution, so we use our big T, our period. Now we can apply Newton's second law here. If we remember that force equals mass times acceleration. Now in circular motion, there's going to be a little c here, and our A sub c equals that, v squared over r. So when we're talking about this force for circle stuff, that's going to be our centripetal force. It always points towards the center of the circle. Centripetal literally means, we translate it from its Latin, means center seeking. So it always points towards the circle, depending on where we're at. Sorry, it always points towards the center of the circle. Always go right towards the center. It's always seeking the center. Centripetal force is the magnitude of the force required to maintain uniform circular motion. So in order to maintain this motion in a circle, we have to have the centripetal force. So you can see the F sub little c always goes towards the center of the circle. As I said, centripetal literally means center seeking. So the force or forces needed to bend the normally shaped path of a particle into a circular or curved path is called the centripetal force. It is a pull on the body and is directed towards the center of the circle. So we can feel it pulling us towards the center of the circle. It's how we go in a circle. So without a centripetal force, an object in motion continues along a straight path. This should be with a centripetal force, an object goes in a circle, and this one should be, it goes in a straight path. So we can see here, there's this little chunk of wood that is causing the inward force on this tennis ball. So it's able to go in a circle. But on this guy, there is nothing to cause an inward force, so he just keeps going in a straight line. We can also see this if we take a candle, put it in a little cup, which I'm going to do in class someday, and you spin around in a circle. That flame will point towards the center of the circle because the centripetal force is pulling it inwards. Kind of neat to see. All right, some people will get confused with centrifugal force. We don't like the F word in physics. It's not a real force. It's only a feeling that's caused by your inertia. So your body feels like it wants to go to the outside. That's the centrifugal force. But it's not a real force. It's just something that we feel because our bodies have mass and want to continue in a straight line. So we can see here that our velocity is always changing. It's always pointing in a different direction. And our acceleration and our, in this case, tension force, which is a centripetal force, is always directed towards the center. So if we have a smaller velocity, you just see the period's just longer. It takes a lot longer to go around that circle. So we're spinning a ball on a string. It's going to take a little longer time to go around that circle with a smaller velocity, which makes sense. If we have a smaller mass, it's going to go around a little faster, which makes sense. More force on a smaller mass is going to cause a greater acceleration, so it's going to spin faster. If we decrease the radius, we are also going to shorten our period of revolution. And force, you see the force stays the same. It's the same length over here as it is here. But our radius is smaller, so we go around the curve faster. All right, so in these pictures, what force or forces provide the circular motion in these guys? So it's easy to say they're all centripetal forces. We have a centripetal force going that way. We have a centripetal force going this way. We have a centripetal force going that way. But we give specific names to these different types of forces. So all the directions of these forces are always toward the center. And can often be more than one force, but we're only going to focus on one per problem. And it can also be components, which we're going to talk about when we get to banked curves. Banked curves. So what provides a centripetal force? So in that picture, there's a string with a weight on the end. Anytime you see a string, it's going to be a tension. Here we have a banana, which is probably just supposed to be the moon, and it's going around the Earth. Gravity is applying the centripetal force. In this picture, the car going around a curve, there's friction between the tires and the road, and the friction is causing the centripetal force in this case. And if we're talking about banked curves, didn't really like a banked curve, but in this case, we have a ball resting on a flat surface, and we know that the force, normal force, always acts perpendicular to the surface of whatever object, or whatever surface the object's resting on. So if you notice, the normal force is going to keep changing. It's always going to be pointing towards the center. So in this picture, it's normal force supplying centripetal force. It's because centripetal force, it's nothing new. We already have worked with tension, we've worked with gravity, we've worked with friction, we've worked with normal forces. So centripetal force can be any one of these forces. So when we're doing our problems, you can't solve for centripetal force. You're always solving for one of these forces, or you're given these forces and you got to find something else. So here's a quick little question. Suppose two identical objects go around in horizontal circles of identical diameter, but one object goes around the circle twice as fast as the other. The force required to keep the faster object in circular path is what? So if you said the answer is E, you would be correct. Because as the velocity increases, the centripetal force required to maintain the circle increases as the square of the speed. So remember our centripetal force equation, mass times v squared over r, because our centripetal acceleration equals v squared over r. So if we double v, we're having mass times 2v, the whole thing squared, over r. That's going to equal 4 mv squared over r. So that's why the answer is E here. So this time, two identical objects going around that same circle, the same speed, the diameter of one is half of the other. The force required to keep the object on the smaller circular path is what? So we go back to our equation, F equals mv squared, but this time we have 1/2 r. That's going to be force equals 2 mv squared over r. So we're going to have twice the force. So the answer is D, basically for everything I just told you. You can read that if you want, pause it. And another one, two identical objects going around circles of identical diameter and speed. One object has twice the mass of the other. This is an easy one to figure out. Do the same thing, centripetal force, so it should be C, equals 2m this time, because we're doubling our mass, v squared over r. Therefore, it's just D, it's twice. So I said tension can supply one of our types of centripetal force. So if the person swinging this airplane doubles its speed, what happens to the tension in the cable? So we double the speed. Remember, force equals mass times acceleration, but in our case, centripetal acceleration, so we use mv squared over r. So if we double the velocity, we're quadrupling the force. Because we're putting a 2 in here. We got to square the whole thing, so it ends up being 4v squared, so we're 4 timesing the force. Alright, so kind of a little review here. Here we have the moon going around the Earth. We can see its acceleration and its net force always point inwards. Its velocity, linear, is tangential to the curve. So remember I said centripetal means center seeking, and we always put a little sub C on these things anytime we're talking about stuff in a circle. So we have centripetal force, we have centripetal acceleration, because we can also find its tangential, which this is not going to have a C on it, because it's going in a straight line. So our velocity, our tangential velocity, is always perpendicular to the net force and acceleration. So we see here all these guys perpendicular to each other. So what would happen if I'm swinging a ball on a string and I cut the cord? Which path is the ball going to take? So this object, it's on a string and it's going clockwise. Alright, so if I cut this ball, or cut the string at A while it's going clockwise, which direction is it going to go? Now it's always going to go, it's going to follow the tangential velocity. So at point A, we're going to have E. So if I cut that string, the ball is going to go straight that way. At B, it's going to go straight down. So this is B. And at C, it's going to go kind of off like that. So this is C. Acceleration vectors at each point. So we're going to have different acceleration vectors. Acceleration at A, towards the center, so it's this guy. Acceleration at B, towards the center, so it's that guy. And at C, towards the center, so it's that guy. Now the force vector is in the same direction as the acceleration vector, so all these guys still hold true for the force vector. A few things to consider before I let you go. We're talking about rotation. We're talking about the axis inside an object. Like if I spin a ball on a table, the axis that ball spins on. So the Earth just rotating, once every 24 hours, that's its rotation. But if I talk about a revolution, it's an axis outside of the object. Like the sun is kind of the center of our axis of revolution, because the Earth goes around the sun, so the axis is outside of the Earth's diameter. So rotational speed can be found by the number of revolutions divided by the time, so the revolutions per second. The period is just going to be the inverse of this rotational speed, so it's time divided by numbers of revolution. And our linear velocity, as I said before, is 2 pi r, because that's the distance we go around a circle, the circumference of a circle, divided by our period. So what affects the speed of a ball tied to a string moving in a circular path? We said the tension, the mass, and the radius from a previous slide. There's the end of the period. So we're not going to worry too much about polar or angular stuff. We're just going to be worried about linear and rotational. Make it a little easier on you. It's easy to convert rotational speed to linear velocity. So for example, the spinning ball in the above picture has a string radius of 0.5 meters with a tube. There are 5 revolutions in 2.5 seconds. So that gives us 2 revolutions per second. So this is my rotational speed, and I want to convert that to linear velocity. So if my radius is 0.5, my time, or my period, is 0.5 seconds per revolution, because it's the inverse of that last guy. So it was 2 revolutions per second is my rotational speed. 1 over that will give you our 0.5 seconds per revolution, which is our period. Now we need to convert this to linear speed. So my linear velocity equation equals v equals 2 pi over t. So now I know what my big period is. So 2 pi times the radius divided by the period, I get 6.28 meters per second. The end.